So two kinds of Fourier series I have told you. What are the two types of Fourier series, dear students?
Trigonometric and exponential.
Trigonometric Fourier series, and the second one is exponential Fourier series. Just I have a question. Why Fourier series? Why Fourier series? Do we have a relation with the concept of orthogonality here, which we have seen in the first unit? Hmm?
Sir, in order to find out periodic signals of multiple frequencies, we use Fourier series.
Yeah. So to easily identify the frequency content of any periodic signal. So if I take an example of a periodic signal x like this, sine of C2t. Do we need a Fourier series to represent this periodic signal? How many frequencies does it contain? How many frequencies does it contain? Does the signal contain? Only one frequency it contains. Am I right? X of t contains only one frequency. And that frequency is, you can compare that with sine 2 pi f naught t. And comparing these two, you will get 2 pi f naught is equal to 2. You can cancel 2. And from this, f naught equal to 1 by pi plus. Now, can you see that this signal contains only one frequency?
Yes, sir.
Yes. Now, for such signals, there is no need for representing that in the form of Fourier series. Now, I will show you one more example. X of t is maybe, I told you an example of a prism. Do you remember that?
Yes, sir.
Okay, right. The prism example. So if you observe that when I give as an input white light, what do you observe in the output?
Seven
Seven
different
different
colors.
colors. Yeah.
So this is actually understood as only one frequency, but it is a combination of seven different frequencies. Okay, until unless this white light passes through this prism, you can't say that it is a combination of seven frequencies. So just I want to say that this is an analogy for Fourier series. This is a Fourier series. Your prism is acting as a tool of Fourier series, that it is easy for identifying the different frequencies present in a single periodic signal. Hope you got me now.
Yes, sir.
Okay, right. So first one is a trigonometric Fourier series. And you also know how to represent that. Whenever I place a symbol like this, that means the signal x of t is periodic. And the symbol name is, I think I have asked you once. The symbol name is tilde. Don't know need to remember this, but whenever you see like this, it is periodic signal. So trigonometric Fourier series is a weighted sum of harmonics. You remember this statement which I have told earlier?
Yes, sir.
Yeah. So this is how we represent the trigonometric Fourier series. Okay. And you should also see here there is 1 actually. So this 1 cos n omega naught t and sin n omega naught t. What is this set called as?
Complete set.
Complete set of mutually orthogonal functions.
Perfect. So this set is a complete set, or you can also call it as closed set of mutually orthogonal functions or signals. Orthogonal signals. So you can see that this one, n varying from 1 to infinity, you get set of cosine functions. N again varying from 1 to infinity, you get set of sine functions. So all this set, whatever I have represented, this is a complete set of mutually orthogonal signals. Fourier series concept is itself representing any signal in terms of the weighted sum of the harmonics, frequency harmonics. N equal to 1, first harmonic; n equal to 2, second harmonic; n equal to 3, third harmonic; and n omega naught representing the nth harmonic. So here A naught, An, and Bn are called as Fourier series coefficients. So this is the representation of trigonometric Fourier series. This is how we represent trigonometric Fourier series. Whereas in that you see the weights A0, An, Bn. We call them as the Fourier series coefficients. Now, can anyone recollect how to calculate? Maybe I want to have a clear recollection. Do you remember that we have represented like this in terms of n functions? Maybe in between we have got gr also. Do you remember this representation?
Yes, sir.
Yes, sir.
Okay. In that case, we found an expression for CR, T1 to T2, f of t, gr of t dt by T1 to T2. Remember this?
Yes, sir.
Okay. So we will use the same formula for finding A naught, An, and Bn. Now, what is the function which is behind this, which is beside this A naught? What is the function which is beside this A naught?
1.
Constant function 1, right? And what is the orthogonal signal which is beside An?
Cos and
Cos
omega
and
naught.
omega.
And what is the one which is beside Bn?
Sine and omega naught t.
Sine. Nice. So keeping those functions in mind, maybe I can recollect again. One for A naught, cos n omega naught t for An, and sine n omega naught t for Bn. We will use this formula for finding these coefficients. A naught equal to. Now, since I am talking about periodic signals, we will consider it is over a period. It can be either 0 to t naught, or it can be from minus t naught by 2 and t naught by 2. Now, this is f of t. And what is gr in this case when I am talking about a naught?
1.
1. Nice. So gr will become 1 here, dt by integral over a cycle. What is gr? It is 1. So 1 square, it is 1, right? Now, can you please tell me what happens? Integral t naught by 2 and t naught by 2. f of t into 1 is f of t dt. And what is denominator simplified?
T naught.
T naught. Okay, because it is 1, you'll get, with applying the limits, you'll get T naught. So can you please tell me now what is the final A naught?
1 by T naught into integral minus T naught by 2 to T naught by 2 f of t dt.
That's it. Now, isn't it easy that we are using the formula which we have derived in the first unit? Now, can you help me in writing for an the same? Integral minus T naught by 2 and T naught by 2. Done. Next, f of t is a function. Now, what should I write in place of gr of t?
Cos n omega naught t.
Exactly. Cos n omega naught t dt. And what about denominator?
Cos square of n omega naught t dt.
Cos square of n omega naught t dt. Now, can you please simplify the denominator and tell me? And before simplifying it, I want to say that omega naught is, you know it, 2 pi f naught, and this is written as 2 pi by t naught. This you can use for simplification. Please simplify the denominator and tell me. You do it in your books and tell me. Meanwhile, I will write the numerator as it is. Simplify the denominator and tell me. I will wait for 2 minutes. Maybe I can help this integral minus t by 2 cos square of n omega t dt is, I can write this as 1 plus number. I think now it will be easy for you to simplify. The first one is t by 2. Maybe I can write this 1 by 2 by 2. What is cos integral?
Sine.
We'll get 2 also. Okay. Now you have to apply the limits minus t naught by 2 and t naught by 2. And here simplifying this, please make use of omega naught equal to 2 pi f naught, which is equal to 2 pi by t naught. Simplify it and tell me what value you get.
So T naught by 2.
Yes, you will get t naught by 2. So denominator minus t naught by 2 and t naught by 2 cos square of n omega naught t dt. You will get a result of t naught by 2. So this result I am using here to write it as t naught by 2. Now can you please tell me what is the final an? Can you see what I am writing now?
Yes, sir.
Okay. So this will become the formula to find the an coefficients. Now, can you please similarly tell me how to find bn? Minus t naught by 2 and t naught by 2 f of t,
F of t sine n omega naught t dt.
right, sine n omega naught t dt by integral over a cycle. Here it is,
Sine square
yeah.
n omega naught.
Now simplify the denominator and tell me
T
again.
by 2.
Yeah, you'll again get t by 2, so that can be represented as 2 by t naught integral or this 2 by t naught integral minus t naught by 2 and t naught by 2 f of t sine n omega naught t dt. So finally, a naught is 1 by t naught. Can I write like this over a cycle?
Yes, sir.
Okay. F of t dt an 2 by t naught integral over a cycle f of t cos n omega naught t dt, and bn will be 2 by t naught integral over a cycle f of t sine n omega naught t dt. So why I am not mentioning minus t naught by 2 and t naught by 2 is you can evaluate a naught, a and bn not only in between minus t naught by 2 and t naught by 2, you can even evaluate that between 0 and t naught. Hope you understand.
Yes, sir.
You can even find that coefficients between t naught of 2 t naught. So the limits of the integration for the trigonometric Fourier series, or it can be an exponential Fourier series, whatever it may be, the choice of these limits should always be a time period or one cycle. And the choice of these limits should be in such a way that the limits of these integrals should be selected in such a way that you need to evaluate less number of integrals. Okay, less number of integrals you need to evaluate. That is how you need to make a choice for a naught, a and bn. So recollecting once again, trigonometric Fourier series, maybe I can write f this. Okay, because I'm using f in the formula, I'm writing this as f. Okay, so trigonometric Fourier series is all like representing any periodic signal as a weighted sum of harmonics, and you can see that this one cos and sine all become a complete set of mutually orthogonal signals where a naught, an and bn are called as Fourier series coefficients, and we have used the formula which we have derived in the first unit to find the coefficients. Why only this formula? In the sense, this formula we have derived by reducing the mean square value of the error function. Do you remember that?
Yes, sir.
That's why we are using the same formula for finding the coefficients a naught, a and bn, and finally you have got the respective formula for a naught, a and bn. Right. Problems we will solve in the classroom. There is a need for me helping to solve. So we will go for the second one, that is an exponential Fourier series, and we will close today. Shall I proceed for this exponential Fourier series? So any periodic signal f of t can be represented as a weighted. So now what is fn? What are these A naught, A and B and Fourier series
Coefficients.
coefficients?
Coefficients of
Coefficients, right? So these are the coefficients of trigonometric Fourier series. Now, how many coefficients you have in exponential Fourier series? Only one. That's
yes,
it.
sir.
That's it. So this is clearly understood as the weighted sum of harmonics. The same explanation. Now we have to find Fn. Can you use the same formula for writing that, representing or finding the expression for Fn? Now tell me, minus t naught by 2 and t naught by 2. The function we need to represent or use in approximation is f. And what is the function here I need to write?
E power
E power, see here, just I recollect again. Yeah, a naught, the function beside it is 1, right? An, it is cos. Bn, it is sine. It is a Bn is a weight for the sinusoidal functions. An is a weight for the cosine function. A naught is a weight for the constant function 1. Similarly, this Fn is a weight for
E power j
exponential function power
uh,
j naught t.
for the complex exponential function. So that's why I'm writing here e power of j n omega naught dt. But there is a small change we expect. What is that change? I think you don't remember, but I'll tell you. We have also seen orthogonality in complex functions. Do you remember that? Or orthogonality in complex signals.
Yes, sir.
In that case, the expression for CR is changed, somewhat changed. What is that change? Maybe I don't write now like this. I will mention the same formula. Integral t1 to t2 f of t. And here, in place of gr, you'll get the conjugate of gr in the case of complex signals. And next one, t1 to t2, you will get gr of t multiplied with gr conjugate of t. Can you find this in your book?
Yes, sir.
So t1 to t2 f of t gr conjugate, and gr multiplied with its conjugate becomes
Mod gr of
mod
the
gr
whole
of t square dt. So this is a formula we have to use now, because the functions we are using for approximating are not real functions, they are complex signals. Now tell me, what change will you expect now? What is a conjugate of, what is a conjugate? What is its conjugate?
E power minus j n omega naught t.
Exactly. And the denominator, it will be minus t naught by 2 and t naught by 2 e power of j n omega naught t multiplied with its conjugate e power of j n omega naught t, its conjugate t. Now simplify this, you will get, so fn will be equal to, numerator you have minus t naught by 2 and t naught by 2, f of t will be the function, conjugate will be e power of minus j n omega naught t dt, and denominator, tell me denominator.
1, sir.
Yeah, it is 1, right? Okay, it is 1 because we have multiplied this e power of j theta with its conjugate, that becomes e power of minus j theta. So e power of j theta, power in power you observe theta minus theta, that becomes e power of 0 becomes 1. So this will be the constant 1 dt. Now tell me the final expression now for fn.
1 by t naught integral
Nice.
minus t naught by 2 to t naught by
By
2
2.
f of t e power minus j n omega naught t dt.
Nice. This is how we use this formula for finding the Fourier series coefficients in exponential Fourier series. Okay, and so if you are supposed to solve a problem on trigonometric Fourier series, you need to find a0, an, and bn. If you are supposed to solve a problem on exponential Fourier series, it's enough. You can find only one coefficient, that is fn. Right? So I have a task for you today. Online lo kuda task ఏంటి అనుకోవద్దు. You have a0, you have an and bn expressions in the case of trigonometric Fourier series. In the case of exponential Fourier series, you have fn. I need the relation between, because why I am talking about relation, because e power of j n omega naught t, as per the Euler's relation, it can be represented as cos n omega naught t plus j sin n omega naught t. And this relation leads us to get a relation between trigonometric Fourier series coefficients and exponential Fourier series coefficients. Did you understand the task today?
Yes, sir.
Right? It is very simple. You can write. So I want a0 in terms of something else, that is in terms of trigonometric Fourier series. I want an in terms of fn, an in terms of fn. This you can think. And I also need bn in terms of fn. Similarly, I need fn in terms of an and bn, f minus n in terms of an and bn. Maybe I can give a clue here, a0 in terms of f. Got it? Maybe you can
Yes,
also
sir.
give clue here in terms of fn and f minus n. Fn and f minus n. Why minus n? Because the limits here you see for exponential Fourier series, you can see n is negative till positive. Okay? So this is the task today, representing. First do this, then you can try for the others. It will be easy for you. Right?
Yes, sir.